So welcome back. Now we have the lightning talk session. It was before the lunch, but we decided to move it after. And today we have like 6 talks. We have 2 demos from StorPool and Stefan Kooman from Bit.nl. Then we have Chris from BlackBerry that will show us some development they did with the OpenNebula hooks and VM events. And then Alberto Picón from TodoEnCloud will talk about the Cfs File System. Lorenzo, he had to left, and he did a virtualized lightning talk. So we have a video from him. And it's called Hyperconverged Infrastructures and Mushrooms. And the last talk is another European project called PANACEA. So let's start. You can use one. Probably a lower one.
I need my, yeah. Let's do this. Hey everyone, I'm Boyan. How are you? Awake? Eaten? Cool. So I'm here to tell you about StorPool. And I'm not going to do slides. I hate slides. So here's my agenda. So what is StorPool? StorPool is a high-performance scale-out storage system, which is used primarily for hosting of virtual machines, for hosting a virtual machine live images. Like Ceph, at a very high level, architectural level, it's like Ceph, but when you dig deeper, it's a completely different system. So it's let's change this. Thank you. So, test, check. No, not yet. Okay, sure. So when you dig deeper, it's a completely different low-level architecture. So different on-disk format, different network protocol, different way of check, cool. Different way of doing things. It's usually used with a cloud management system like OpenNebula, and we have a couple of other hookups like ONAP and OpenStack. And we have a kind of good mixture of customers using these 3. There's some feedback here. Okay. Right, so why would you want to use StorPool? The main reason is performance. So let's close this. No, need to move this a bit to the left, I guess. Is this too small letters, guys, everyone? Too small, too big? Way too small, okay. I'll try to fix that. Better? Okay. this up, move it to the left a bit. Okay. Sorry about the delay. You just need to set this screen up like I wanted. All right. So, what does performance mean? How many of you are familiar with FIO? FIO? Okay, good quarter of everyone in the room. So FIO is a very popular, mostly block device performance testing tool. And you can ask it, in this case, to do sequential reads with block size of 1 megabyte and I/O depth of 32. And on a StorPool block device, it would do something like this, right? So if you're not familiar with the output, this is in megabytes per second, right? This is single initiator, 100 gigabyte volume, fully allocated on a fairly small StorPool cluster underneath. So how large is that cluster? It has 12 SSDs and 12 hard disk drives in just 3 nodes, right? It's not a huge cluster that we somehow spread this load across the whole thing, right? So people choose StorPool because of performance and efficiency, right? It's because it allows them to do things like, if we did, say, random reads 4K with a large I/O depth from a single VM, you can think of this like a single VM. It can do 200,000 IOPS, okay? So it's somewhere here in the report. There it is. Right. So what does this kind of capability allow you to do? We heard on some talks during the conference, things like it doesn't make sense to put databases on your shared storage. With StorPool, it does. Okay, it doesn't make sense to put your swap file on your shared storage. With StorPool, it doesn't matter. There's simply enough performance down there for you to use this as if it was a local SSD, right? And another thing we heard on a couple of talks is storage QoS. QoS is a big issue. So if you have competing workloads, they interfere with each other. With StorPool, what you can get is, first of all, so these are the volumes. This is the volume we're working on. If you say volume oconf IOPS 1000, that just drops down to 1000, and you're done with it. Okay? And if you just remove the limit, it goes back to 200,000 IOPS. So this is limits, and you also have fairness between volumes. So if you have 2 workloads, we would give them equal disk time. And in terms of OpenNebula integration, so this is the list of volumes in StorPool. I'll try to make this big enough so you can see it. Don't need this anymore. So this is the list of volumes in StorPool. These are the IDs of images. In this case, this is image 8, and image 8 is a non-persistent image, and it's used by VM27, right? So for non-persistent images, you get the base image and the current state of the VM. For persistent images, you just get one volume in StorPool. I don't need this. This is okay. And if you say create a new image, say I want it on StorPool, I want it persistent, it's going to be a data block, empty, and it's going to be 10 gigabytes, like this. Okay, click create here. Oh, I forgot to give it a name. Okay. Create. And there is a new volume in StorPool, right? Take that, delete it. that volume disappears. Okay? Simple. And then the other thing I wanted to just to give you an idea of how, how does this integration work? What kind of things does OpenNebula instruct StorPool to do? Sure. This is the list of attachments. So this says this volume is presented on this host and this volume is presented on this other host. In this case, we have a running virtual machine on host 8. Sorry, on host 2. And if we find the VM here, there it is, running on host 2. If we take that and live migrate it to a different host, like this. So it should move from host 2 to host 3. What happens is first OpenNebula instructs StorPool to attach that to a different host, then migrates the virtual machine, then detaches it from the previous host. Right? So it's like any other shared storage system. The volume is only presented where it's needed, and we orchestrate together with OpenNebula, we move the attachment from one host to the other when that's needed. And I think that's mostly from me. I think I have time for one question, or we don't do questions?
Probably at the end.
Yeah. Questions later then. All right. Thank you for your time.
Just click it. I didn't bring my own. Can I use the one as well? Yeah. So did it have a network connection, or do I have to use? Yeah. There we go. So yeah, like Chromium is okay. I think I should be able to. It's in Spanish. So, okay. Let me see. Where's the slash in this keyboard? Oh, here it is. Right. NebulaConf. So this should work. Disappears. There we go. Like full screen. Yeah, there we go. Is this working? Is it working now? Yeah, okay. I can hear myself. I'm Stefan Kooman. Actually, do have a pointer somewhere. Oh, here it is. What is the pointer? All right. So I'm from Bit. It's a small hosting company, a small data center in the Netherlands. Well, I'm gonna give a small talk about the proof of concept we did with VXLAN in a test environment. So what will I talk about? VXLAN, why we want to use Routed Multicast, and how it works with OpenNebula. So why would you actually want to use VXLAN? Well, if you want to stretch layer 2 networks between data centers, or even within a big data center, and even spread quite far apart, could be even on the other side of the world, then, well, there's some ways to make it appear for a virtual machine that it's in the same virtual or same layer 2 network. And well, one of the ways to do that is with VXLAN. There are a couple of other solutions, but VXLAN has the benefit of being in the hardware hardware support of switches and routers. If you have some recent hardware, so it's actually invented by by VMware and Red Hat and some other companies to come over the scalability limit of VLANs. You can only have like 4K of VLANs and isolated networks. And with VXLAN you can reach like 60 million. So if you use VXLAN, there's no need to stretch physical layer 2 network between data centers or within the data center. Stretching layer 2 networks is, well, that sucks. It has lots of issues. You try to avoid that. Well, at least in our environment, it's easier to provision would be easier to provision a VXLAN than to provision a virtual network. If you want to have a virtual network, I first have to ask network engineers to provision the VLAN on all the switches and routers and hypervisors, and well, now I can just avoid that and provision it from OpenNebula. So why routed multicast? Well, if you don't have a network controller, you need multicast. Otherwise, VXLAN doesn't work. It's based on multicast. So why would you want to route multicast? Well, it's again to avoid the layer 2, to have a flat layer 2 network, to have your host participate in multicast routing. So if you use routed multicast, you can actually just route it through your data center and between data centers, and well, that makes more sense. It's easier to scale and use all kinds of layer 3 redundancy. That is most of the times in place already. So how it works with OpenNebula, it makes use of the Linux kernel support for VXLAN. It's in, well, from 3.7 on, it's in the Linux kernel. It makes use of a one-to-one mapping of the VXLAN ID. It's like a VLAN ID, but then a VXLAN ID. And it will map it to a multicast group. So VXLAN 1 would map to, if you have like a privately administered multicast range, it would map to this address. There we go. So here's an overview of how it works. There's a virtual machine over here, with the macro is over here, and it wants to commute, and well, we power it up on this host. We do the same for this virtual machine on this host, and this virtual machine wants to talk to this one. So first it will generate the broadcast packet, get wrapped into UDP, and at that time it will send an IGMP join to the switch. Well, this host will send this packet to the multicast group address, destination address of the VXLAN ID is 50 over here, so it's going to be this destination multicast group, and it will have the source address of this host. Well, all the hosts that participate in the multicast in this multicast group that has actually VMs running with virtual machines running in VXLAN 50 will get this packet from this switch. It's only the hosts that have an interest in actually receiving your traffic will have joined the multicast network and will receive this packet. Well, the host will de-encapsulate the packet, strip off the extra headers that are added over here. So this is the VXLAN overhead, and you'll just have this layer 2 IP payload, and it's delivered to this virtual machine. So actually it's just a tunnel, and it uses multicast in a clever way to avoid too much traffic going through the switches. If one VM wants to talk to another VM. So unknown unicast and multicast traffic from the virtual machine will follow this route. As soon as the tables have learned the destination and source MAC address of the virtual machine, then it will all the unicast traffic will directly go from this virtual machine to this virtual machine, from this address to that address. So it's not gonna go by multicast. So in OpenNebula, the driver code is pretty simple, but we had to do a little hack, because if you want to route multicast, then you actually have to add the TTL. Otherwise, traffic won't go out of your host. It will be dropped at the host level. So we had this TTL here in the code, and you will actually, these are the things that will be executed on the host itself. A bridge will be set up. then this is the VXLAN creation on a specific VLAN. And then actually the virtual machine gets attached to it. So this is the XML code from the deployment. So it's bridged to VXLAN 50. And if you look it up on your host, you will see you've got a VXLAN 50 bridge. This is the interface for it. And the VNet is connected to this VXLAN bridge. Well, that's about it. We have got some configs online if you want to replicate the setup. And well, there's like 16 million IPs you can use in the multicast network to do this. So you can actually well, get over the VLAN limitation, and really easy. So that's about it. Now let me finish it off. All right.
Okay, next talk is Chris from BlackBerry. We are going to use this one.
I am Chris from BlackBerry. We've been an OpenNebula user for quite some time now. Unfortunately, most of our infrastructure is confidential due to company policy, so we haven't really been able to come out with our user experience. But I can come out with something we do that, or I want to share something that we do that I can. So I've heard a lot of talk about hooks the last few days, and we had a lot of requests from our internal users on how they manage VM events. And usually it comes back to them wanting to implement a hook into our system. Now, unfortunately, we don't want to manage dozens of scripts or look through the source code of everyone's script that they give to us. So we wanted to move that to an external system. So this is what we did. Here are just some use cases on why users want to use hooks. There's a whole list. You could probably go on, a couple hundred. Anything from alerts to infrastructure services, elasticity, load balancers, automation. So what we did was we're pushing hook events into a message queue that we allow the users to subscribe to. Every user will receive a full copy of their VM template if they choose to receive it. What they'll do is they'll log into the broker, the message queue broker, create a queue and say we want to receive messages that are tagged VM creation, VM deletions, VM failed. So they create bindings for that. When that hook would get triggered, that message gets sent to their queue and they're able to consume it. As well as receiving their own events, we can also use this for services. So within their VM template, they can also say, I also want to send my VM template to this service. This is just some details on the message that gets created. It's all AMQP specific type stuff, but the topic exchange that gets created automatically is one for each user to OpenNebula.username. If they have a service, service.servicename, and then a routing key will be the VM state. So that'd be VM created, VM done, VM failed, VM unknown. They can subscribe to specific events if they want to receive those. Down below in the body of the message, users can specify what they want services to receive. So for example, in here in the notify equals DDNS equals none, they're not sending any of the context template to that service. Some users have confidential information in their context keys or something they might not necessarily want or need the DDNS service to know about. So that will get stripped out of their VM template before it's sent there. So that's it. That's what we're doing. Hope it helps someone out.
Thank you. Thank you. The next one is Alberto from TodoEnCloud.
Hello, good afternoon. My name is Alberto Picón. We are a small company in Spain. We have our data center in Tertian in Madrid. And we started our operations in 2011. We started from the very beginning using OpenNebula as our cloud core management. And when we started to decide what kind of storage system we're going to use, we tested several things, and one of them was the Cfs File System. I don't know how many of you have tried it. Any? Of course, StorPool. But anybody of you are using Cfs? Okay. I think it's a very interesting file system. We have tested it a lot, and I think you will find it interesting. The Cfs features and architecture are extremely large, but I think that the Cfs file system has been created especially to build to scale. Has been built to scale. It has the capability to manage 256 quadrillion zettabytes, which is a huge amount. And it has been developed using, having in mind the data integrity, and one feature that I like the most, which is copy and write file system. Every write is transactional, so every block that is written in the data store is confirmed and is consistent. We have tested this file system lots of times, doing crazy things like powering it off in the cables in extremely used peaks. And we didn't have any kind of corruption of VMs, of the data inside of the VM. This is really important for us because we offer to our customers disaster recovery programs. So as we will comment later, this is a feature that we use to restore logical dumps from databases, which is very interesting. The architecture goes though to adaptive read cache. This is in RAM. We have a level 2 ARC, and this ZFS intended log, which is a write cache. This architecture enables a way to improve the disk's performance using SSD caches, doing reads and writes, and to provide several ways of offering performance to the customers depending on the VM usage. Okay. It offers POSIX file system on volume block mode, which is very nice to provide live migration, file system, share file system, sorry, and volume block mode to expose iSCSI targets to VMs or to share data blocks too. It has compression, deduplication, snapshotting, send and receive, which is very important for backing up. In the morning, we saw a Bacula solution, and I think this could be a very nice feature to mix with your solution, especially to avoid file system corruption. To create a snapshot before, launch the backup, even when the machine is working. As you already know, the data store model of OpenNebula enables a way to expose common repository with links, and this is data store. We use this to store the VMs of a customer. Every data store is a customer for us, so this enables us to offer what we say. We are Postgres fans too, so we say we call it OpenNebula Cloud Point-in-Time Recovery. Okay, so this is a way to offer our customers a way to roll back their whole cloud to a specific point in time, which is very important for us because sometimes we offer our customers a way to snapshot every hour automatically their clouds, and the possibility to roll back to a very specific time to dump a database, a logical database. We have tested this in Postgres without row corruption, without file system corruption. We have built, this feature enables us to create pre-production and development environments using snapshotting and cloning, which is a really nice feature. We have a way to create from a snapshot. We can create a clone which is possible to read and only stores the deltas from the snapshot which come from. Okay. Every snapshot that you do and the whole file system has compression enabled, so the amount of space that is wasted is real low. Okay. There are lots of things about Cfs. I think the features, especially this one, of not only creating snapshots, we can send those snapshots to another storage system and send first a full, complete file system and then the snapshots. It's a good choice for replication too. Okay? And that's all. Hope you find it interesting.
Thank you.
This is a question. Ceph over Cfs. Gluster over Cfs. I've read lots of things about it, but I would like to know what's your opinion about this?
Okay, we can talk about that in the open discussion. So. So, sorry. As I said before, the next talk is a virtualized talk.
Platform, in the sense of the body of
Okay, it's from Lorenzo, and I'll let him start.
Let's talk about hyperconverged infrastructures and mushrooms. I'm Mr. No One. I'm just a natural scientist that happened to be a sysadmin. And as a brand new father, I started to understand what really was the meaning of the word time and the value of it. And also got an idea on how much the uptime and reliability in the IT department can impact an sysadmin mental health. Then, in 2012, I met OpenNebula, and I met Carlo and the NodeWeavers project. Then the path was clear, for me at least. I come from natural sciences. I'm supposed to know more about beasts, plants, rocks, and mushrooms, rather than a cloud computing, DFS, hypervisor, software-defined networking, and so on. When I thought as a scientist, as a natural scientist, about a server or a service that I had to manage, I wanted it as robust as the most robust thing I've seen in nature. And that's mushrooms. But not really that form, in the sense of the body of the mushroom itself. This form here, the mycelium, so the network underneath the soil. A fungus is a unicellular being that has the form of a network of cells, entirely made by the same cell, cloned X times. Every cell is capable of morphing into a kind of differentiated cell. It can be considered as staminal, and any single cell can do all the kind of work that the organism is supposed to do. So, in a hyperconverged infrastructure, you have mycelium, hypervisors, distributed storage, and networking beneath the soil, and then you have the carpophorus, or the body of the mushroom itself, the differentiated shells, that are your VMs, services, containers, files, and whatever. Think of a mushroom body as a virtual appliance for deploying spores. A VDI infrastructure, or your databases, whatever. And actually, you cannot kill a mycelium. You can dig your loam, your soil, or pour some antimycotic agent or whatever, but you'll never really kill it. And it will be able to start growing again from its spores, carrying its DNA, and always carries all the instruction and the resources to instantiate again another complete working mushroom. Fungi are maybe the most resilient beings in nature. Being that said, I want services and virtual services like that, period. For this reason, I joined NodeWeavers, because it was the only thing that I met that, as a mushroom in the woods, survives thanks to its mycelium. And working with NodeWeavers meant using OpenNebula on a daily basis. From my point of view, it's like the nucleus for a living cell. So it's like the nucleus of our mushroom. OpenNebula orchestrates the function of this being that is our hyperconverged appliance. The point is that it's designed to be the nucleus. It does not convert energy it's not its focus. It just manages the function of the cell, and it does it very well. It's not Mr. Do It All. It's focused on the objective. Who produces actually transforms the energy in a cell, in a mushroom cell, is a mitochondrion. That, in a computing cell, are the hypervisors, converting your electricity into your servers to virtual services, to operating systems running. Mitochondria rely on the cell body and the membrane for the uptake of the outside atoms and molecules. Your data, your storage is there. You can see the juice of the cell, the cytosol, as your storage. So I want to adapt this philosophy in designing the infrastructures, and that is a brutal copy and paste of features from nature to data centers and servers. So NodeWeavers is the thing that looked most like a mushroom, and now I use it full time and anywhere, and I can sleep at night, apart when my son does not. And sorry, I didn't mean to be commercial or marketing guy saying good words about the product or the project. I just wanted to share my experience as a sysadmin and a natural scientist to give you a different point of view on computing. And thanks to everyone here, because we had really great time and we enjoyed spending time at this conference as always. Thanks to everybody, and
The last talk is about PANACEA. PANACEA is an European project. For those of you that were here last year, I will talk about it. And the main objective of this project is to build, to design an architecture for proactive autonomic management of cloud resources. So based on the autonomic cloud architecture that IBM wrote, we want to provide self-awareness and self-configuration to the services. That's, we want to allow the virtual machines of a service to be aware of the execution environment. And we also want to allow the VM to trigger actions on OpenNebula and modify the service itself. So what are the components that we are using for this project? Of course, we are using OpenNebula for the cloud manager. We are starting all the virtual machines through OpenNebula. And we are using also one flow to define multi-tier applications, where you can define several roles with several virtual machines and define elasticity rules. And we are also using OneGate. OneGate is the component that is providing the self-awareness and the self-configuration effectors to the service. The thing of OneGate is that you don't need an OpenNebula account to interact with OpenNebula. It's the virtual machine itself, the one that is interacting with OpenNebula. It will be able to retrieve information of itself and of the service it belongs to, and it will be able also to scale the service, to start new virtual machines. So the idea is we define a service, for example, a Hadoop experiment where we have several masters and workers. This is deployed through one flow. Each virtual machine will have monitoring agents that are populating a database. And they also include several agents, for example, the OneGate client to interact with the OneGate server, and some other agents for the overlay network, but I'm not going to enter in detail there. So this service will use the information from the monitoring manager and the information that it gets from OneGate. So how many virtual machines are in the service, what virtual machine, what is the IP of this virtual machine. And using all those information, the predictions models that are generated using machine learning will decide how to modify the service. For example, it could rejuvenate the application, or if he's running out of resources, it could start new virtual machines. So that would be the workflow for a service with the PANACEA framework. What we've been doing during the last year, well, we moved this design to a multi-cloud environment. So there we had two options. We could use a federation of different OpenNebula deployments, or we could use a hybrid cloud, a cloud bursting model, where we have a private cloud with OpenNebula, and we use resources from external cloud providers. What is the problem that we found here is that OneGate does not work with virtual machines instantiated in public cloud providers. So we are extending OneGate to be able to use it from Amazon EC2, from SoftLayer, Azure, and even with vCenter. Other two concepts that we've been talking about and designing and trying to solve is sometimes you need also information of the infrastructure of the service. So if you want to migrate some virtual machine of a service, it would be nice to know what is the capacity of the host that you have available. And also another nice feature is the multi-zone one-flow services. The thing is that when you have multiple zones, the only resource that is shared among different clouds is the authentication part, user groups and ACLs, but resources are not shared between the different zones. So probably it would be nice to be able to define services that use different resources from different OpenNebula zones. that is something that is there, but we are not doing it or implementing it yet, but probably it would be nice. And that's all. This was the last slide and the last talk. So thank you. Probably if you have any questions, we can use the last session, the open discussion session. So if you want to know more about this or any of the talks of the speakers, we can talk about it later. Thank you.